everyone, and welcome to part 8 of the series where I react to the Flat Earth's alternative to gravity, which is Incoherent Electrostatic Acceleration. Note that this time I'm not reacting to anything since we were done with both of the videos by Good Times for All. This time I thought I'd go a bit over the mathematics and a bit over the formulas, and honestly, I kind of want to know what flat earthers would say to that. I would say one of the things that they would say to that is, oh, it's just formulas. But yeah, so yeah, let's just start. I started by, because, you know, Good Times for All, he had this example with the bowling ball, right? Where he said that, well, the bowling ball, it accelerates downwards, and that's due to the incoherent electrostatic acceleration and things like that. And I thought, well, it would be interesting to know what its charge would need to be accelerated by that amount, right? So what I wanted to know, right? On the left side here we have the classical formula of gravity, the Newtonian formula of gravity, which is G times mm, big M being the mass of the Earth and small m being the mass of whatever we are testing here. I assumed the mass of the bowling ball to be 1 kilograms to make the calculations easier. I don't know how much bowling balls weigh, though, to be fair. It's more than 1 kilogram. That I know, but I just did one, right? Alright. And over r squared. As r, I use the radius of the Earth, and I can already hear the flat earthers jump into action, telling me that that's not a thing that I'm allowed to do, because I'm presupposing the radius of the Earth. I'm not, because later I will calculate it with just using the 100 volts per meters. But and you will see that the results are almost identical. But let's continue. So the force that the gravitational force that is exerted is 9.8. I don't even need to go to 9.81. I could have done it with 10. It's just to get an idea of what the charge would be like, right? I'm just going to go for the magnitude. And on the other, on the left, right-hand side here, I have the formula for the Coulomb force, right? Which is 1 divided by 4 pi times the electric field constant, which I have here. I left out the units because it's not important right now. And the Q divided by r squared. Big Q here is the charge of the Earth. The charge of the Earth is, I took it from Good Times for All's own reference, where he referenced physics lectures from MIT by Walter Lewin, where he says that the charge of Earth is around 400,000 coulombs. So that's 4 times 10 to the 5. And what we want to know is the charge of the bowling ball, right? So I calculate the left-hand side, which is 9.8, as we know, and I calculate the right-hand side, apart from the small q, which is 88.6, and so I from that we know that q must be roughly 0.1 coulombs of charge. Now that doesn't seem like a lot, but it is quite a lot. 1 electron has roughly 10 to the minus 19 coulombs. So the amount that this is charged would be absolutely humongous, right? And you can see how high it would be if we use what I did down here. Now down here I have the formula for potential, and in this which potential really is voltage, right? So K, by the way, is the Coulomb constant. The voltage that we would have if we were to grab the bowling ball, right? And if we were just 5 centimeters away, so if we bring our hand up to 5 centimeters to the bowling ball, the potential difference that is necessary would be 2 times 10 to the 10 volts. That's 2 billion volts. You would get the shock of your lifetime. I believe, although I might be wrong, I believe for a charge, for a electrostatic discharge to travel 1 centimeter, I believe you need 2000 volts of voltage. So this would shock you from a few hundred meters away. So yeah, no, that's not happening. This is such an obnoxious charge, so absolutely impossible. It cannot be the reason why things are falling down. It cannot be charge, because the amount of charge that is necessary would be absolutely huge. So just so you know, right? On flat Earth, I calculated it because as I mentioned earlier, they probably say, oh, I used the R value. I don't have to. His own citation with 100 volts per meter, which is the electric field, right? This is the electric field is 100 volts per meter, and the acceleration inside an electric field is charge times electric field over mass, right? So as above, I do the mass of 1 kilogram, and the acceleration that we measure and know is 9.8 meters per second, kilogram times meters per second squared, which is Newton. So again, we should figure out the Q, and the Q here comes out to just shy of 0.1, and that's with roughly, that's with 100, but as I've shown in one of my videos, even the Feynman lectures say that it varies a lot, so it's also not that. It's the same thing. So the reason for the acceleration cannot be electrostatic in nature. Now, another thing that I wanted to do, because it is brought up quite a bit, is the comparison between gravity and the electrostatic force, because I think it's important to get a grip on these things. This is usually the thing that they do. They either take two protons that are 1 meter apart. Sometimes they use two protons that are a few femtometers apart. Sometimes they take two electrons. Sometimes it's an electron and a proton at the typical distance between nucleus and shell. Things like that, right? And you compare them. This is what you do in electrodynamics at the very beginning, to make it clear that gravitational effects do not play a role when you talk about electrodynamics on the scales that we are talking about, right? And you can see it clearly here with the gravitational force you have that many newtons, and with the electrostatic force you have that many newtons. So there's a difference of roughly 10 to the 24. But what I want to stress here is that, of course, if you have things like protons that are very light and have a non-negligible charge of the unit charge, right? The charge itself, like the unit charge in coulombs, is roughly 10 to the minus 19. And the mass is 10 to the minus 27. Well, yeah, of course, there's going to be a huge difference, right? But if you do it with everyday objects, and the flat earthers always say that, oh well, yeah, you know, it's 10 to the 24 times stronger. How can we isolate it? Well, you ground it. When they're grounded, the difference in electric potential is so small that the charges are, unless you're using super specialized equipment, so small that they are not measurable with like a multimeter or things like that. So yeah, that's not even a real question, right? Yeah, there is this difference when we talk about small scales, but as Walter Lewin said himself, mind you, in the source that he uses, as Walter Lewin said, on large scales the force of electrostatics for large objects is so small compared to the huge force of gravity there. When he gave the example between Earth and Mars, that the Earth's gravitational pull on Mars is 10 to the 17 times stronger than its electrostatic force would be. So it's you can completely ignore it, completely, right? And that's a point I want to drive home. This comparison is done for small scales. If you apply large scales, and these masses here, they grow a lot, but those charges here, they don't grow by a whole bunch, because bulk matter usually tends to be neutral. And you won't have a difference of 10 to the 24, but rather like 10 to the 17, but the other way around, that gravity is much bigger. And to end this, I thought I would give a small insight into electrodynamics, the very basics kind of, with the with the Maxwell's equations and what they mean really. And well, first of all, the divergence of the electric field is the charge density. That's this rho here. It's not density, it's charge density. So the thing that carries your charge, and I'm not talking about neutral bulk matter that is made out of protons and electrons. That's still neutral if it has protons and electrons. I'm talking about free charge carriers, like free electrons that are like too much in the metal, for example. I'm talking about these charge carriers divided by the electric field constant. The divergence, by the way, is kind of, you can think of it as some sort of origin. So like, where is an electric field going to come from? Well, it's going to come from some charge density divided by the electric field constant, because that's how nature works. There's a constant involved. The next thing is the divergence of the B field. B's magnetic field is 0. So this might seem irritating. There is no magnetism? No, that's not what that says. That says that there aren't magnetic monopoles. So the divergence of B must be 0. That tells us that magnets are always bipolar. You cannot have a monopole. It needs to have a positive, well, we call them positive and negative pole. Those are arbitrary names. You could call them north-south or 1-0. But the gist of it is that there are no magnetic monopoles. This also follows from the Maxwell equations. And then you have, those two are really the more important ones for the things that we talk about, I believe, is the curl of E. The curl is kind of like a rotation. Is minus 1 over the speed of light, dB dt. That means that the change of the B field over time. And the second one is the curl of the B field, so where a B field is generated, is that one. This is just the displacement current. I talked about this in an earlier video. I will not go through it now. But essentially, it's 1 over c times the change in the electric field over time, plus a constant, kind of, plus a displacement current. So what that tells us is the B field kind of exists if there's a change in the electric field. And if there's a change in the B field, there will be a kind of a curl, so a kind of rotation in the electric field. So static charges. So for static charges, the dB over dt is 0, and the dE over dt is 0, so we just have an E field. So static charges, you have an electrostatic field, an E field. When you have moving charges, so suddenly the dE over dt here is existent, you will have a B field. So moving charges create the B field. If you send electricity through a wire, you can detect a magnetic field around the wire. That's also how they have those nice wire finders, so you can find the wires in walls, for example. And accelerated charges, and I'm not talking, here I said moving charges, strictly speaking I should have put moving charges at a constant velocity. Because here, when you have accelerated charges, so the dE over dt changes, but it changes not at a constant rate, but like at a non-constant rate. That means that the dB over dt will also change. Then you have both an E and a B field. That's what we call an electromagnetic field. This will give off electromagnetic radiation. This is what is used, for example, in a synchrotron to create radiation. Yeah, so I thought I'd quickly talk about that. It's not directly relevant to this incoherent thing, but I thought it's important and it's nice, and you can see it in Maxwell's equations, and I like the Maxwell equations. You can also somewhat easily solve the Maxwell equations and figure out the speed of light. It is in here, but in his original description there were two other constants, which is the electric field constant and the permittivity constant, I believe, or was it the dielectric constant? Something like that. There were two other constants, and then he found out that the speed of light is really inversely proportional to those two electric constants, because he solved it, and now you can just write c down here instead of like epsilon 0, mu 0, but that will, also possible, because some flat earthers don't believe in the speed of light, Yeah, So that's that. I thank you very much for watching for this rather dry educational video. And I don't know what I'm going to do next. Maybe I'll have a little break from YouTube, and I'll see you in the next video. Maybe consider leaving a like or even subscribing. I'll see you in the next one, and thank you so much for watching. Goodbye.